In stats, we may come across certain types of data distributions as the binomial, where we'll have some fixed probability and a fixed number of trials, or the normal, where we'll have some means and standard deviations, and we'll take the data from a scenario and put them into certain equations to find out other pieces of information within that scenario. Yet before we get to those, we may come across some other distributions first. These perhaps referred to as discrete probability distributions. Now, what may make these more distinct from the other distributions, so we're going to deal with them first, is they don't necessarily rely on the same level of equations or special features on your calculators, and then more importantly, the probability of an event may change each time. It's not a consistent, constant probability. Now, before we get into this, we probably want to define a couple of words. Firstly, discrete itself, if we're calling these discrete probability distributions. So for data to be discrete, we're basically just saying that there has to be distinct x values. Usually this will be integers, but maybe it could be at halves as well. The point is, it's not continuous data. Continuous data, it could be any possible decimal on a spectrum. So let's say someone's height. If you were to measure someone's height, obviously there is a limit as to what human height can be. We can only be so short or so tall, yet within that range, people are going to be any possible value. Whereas perhaps something like shoe size would be more discrete, because shoes are only made in certain intervals. You have to fall into one category or another. If you want to double check if something is discrete or continuous, therefore, basically just say, okay, could I have 0.37 of this thing, or whatever decimal you want to come up with? If it seems like you could have any decimal you come up with, then it will be continuous. But if that doesn't make sense, if you have to either be a whole number or fit into a specific decimals, then it's going to be discrete. As for uniform, this isn't going to come up so much, but we should mention it here all the same. The uniform does mean that we have the same probability each time. Now, yes, this does just immediately contradict what I said before about what we're going to be looking at here today, but I'm just saying, as a word to cover in relation to this chapter, kind of while we're looking at discrete data and so forth, we could say potentially that, oh, this particular distribution is uniform, like if you're rolling a dice, a fair six-sided dice. If it's fair, that means that, again, it's uniform, the probability is going to be the same. You have a 1 in 6 chance of landing on each face. The reason why, nevertheless, though, that it can't be used as the binomial is that there are more than 2 possible outcomes unless you're going to phrase the situation in a particular way. But I digress. This isn't really the focus of that being the binomial. We're looking at these probability distributions here, such as what we have below. That the probability of x equaling x, so a capital X and a lowercase x, is... Now here we've got 3 different rows within a curly bracket, and what this is basically saying is that the phrase here on the left hand side of the comma is the equation we're going to use to work out what the actual probability is. And on the right hand side of the comma we have what x values that works for. So here we have k lots of 2 minus x, and this is true if x is any of 0, 1 or 2. And then below that, k times x minus 2 this time, that only works with x as a value of 3. And then there's a probability of 0 of anything else happening. So we have discrete data because only these specific x values work, but in this case it's not uniform because probability will change each time. So if we were to start off with by trying to find k, what we'd have to do with this distribution is say that the sum of all of the probabilities will have to be 1. If you were to add up all possible outcomes, it has to come to a certainty. If it didn't, you either made a miscalculation or you're missing a possible outcome. So, to work out each individual probability in terms of k, we could say that if x is 0, then that would be 2 minus 0, that's still 2. So that therefore is going to be a probability of 2k. Add the probability of x being 1. Well, 2 minus 1 is 1, so that just becomes a single k. And then add 2, or x is 2, so 2 minus 2 is now 0. Well, 0 times k is nothing, so actually we can ignore that there. Moving on to the next example here, we have x equals 3, so put that in here. 3 minus 2 is 1, so again you now have plus another single k. And because everything else has now a probability of 0, this would be all of our possible outcomes. So they must add to the 1. Now altogether this is going to be 4k. So 4k equals 1, and a single k would equal quarter. And now that we know this, we can move on to the second part of the question, where we're told that two independent observations, and independent just means that they're not going to impact each other, of x1 and x2 are made. We'll show that the probability that x1 and x2 equals 5 is 0. And to be clear, the 1 here is not saying that x inherently has a value of 1, or the x inherently has a value of 2 here, just saying it's some first value, some second value. It could be any of these from the possible list, with this capital X here equaling any of the lowercase x's. So if we were to take two of these lowercase x's and add them together equal 5, well, what combinations could work for that? Since we're only taking two of them, it can't be the 0 because you'd then need to add 5 to 0, there is no 5. Similarly, it can't be the 1 because there's no 4 to add to it. So we're left with the 2 and the 3. Either we're looking at x1 being 2 or being 3, and then x2 being the other one respectively. Well then, if we were to show that probability, what we'll need for them to both happen is the probability that x equals 2 times by the probability that x equals 3 for that first way round. Well, the probability that x is 2, let's see, well, 2 minus 2, that's going to be 0, so 0 times k, doesn't matter that k is a quarter, that's just 0. So that 0 is now going to be times by 3 minus 2 is 1, so 1 times k is just going to be a quarter. I mean, again, that didn't really matter because we've got 0 times it, so it's going to be 0. And the exact same thing is going to happen if we do it the other way around. If we'd had the probability of x equaling 3 first, times that by the probability of x equaling 2, you're again going to get a quarter times by 0, which will just be 0. And usually, now that we have two outcomes, you would then add them together, but in 0 add 0, it's just going to be nothing. So again, yes, the probability that if you had two x values and they added together to make 5, the probability that you actually get that happening is 0. It wouldn't. Well, it's this principle then of getting combinations of x's adding together and the probabilities of those. It's that principle that we're going to be using in the continuation of this question here. So finally, complete a probability distribution table for x1 and x2, and so find p, or the probability, that the x1 plus x2 is greater than or equal to 1.3, but less than or equal to 3.2. So, well, first of all, to complete the table, what we're first actually going to need to work out is the individual probabilities of the sums of x1 and x2. So the probability that x1 add x2 equals 0, well, the only two x values here that would add together to equal 0 is going to be 0 and 0 again. So here if we take 0 as your x, so 2 minus 0 will be your 2 times by the k, which is a quarter, so 2 times a quarter is going to be a half, and because we need them both to be 0, you would be timesing by the half again, which gives you a probability of a quarter. So we have a quarter of a chance that x1 and x2 would equal 0. But it could also equal 1. And the way that it would equal 1 is if we had x is 0, then x is 1, or x is 1, then x is 0. Yes, it's the same pair of numbers, but in probability, a different ordering counts as different scenarios, so we have to treat them separately. If we were to do the 0 and then the 1 first, we already know the probability of getting a 0 is a half. And the probability of it landing on a 1, or whatever this is, getting a 1, 2 minus 1 is 1, so 1 times a quarter is a quarter. So you'll end up with a half times by a quarter for your 0 then a 1, but then you'll add to it the probability of 1 then a 0, which would be the quarter times a half. And the reason why you're adding in the middle is because at that point you just have an either or. Either of those situations would fit your criteria. They're obviously not both going to happen. If it's both, if it's and, then you times. If it's either or, you add. Either way, this is then going to end up giving you, actually, once again, another quarter. So you have another quarter of a chance that these two x values, whichever you pick, end up adding together to equal 1. They could equal 2. The way this is going to happen is if you either have a 0 out of 2, or a 2 out of 0, or a 1 out of 1. So we've got 3 situations here. Well, again, the 0 we know is a half. As for the 2, well, 2 minus 2 is 0. So 0 times a quarter is 0. So you're just going to half times 0, add 0 times a half, and then the 1 we said before had a probability of a quarter. So that's then a 1 and a 1 will be a quarter and a quarter. Obviously, the zeros here are just going to make these brackets disappear, so we might as well just focus on the quarter and quarter, which would give us 1/16. Only 1 out of every 16 attempts at this should end up with the numbers adding together to be 2. If we wanted them to equal 3, well, that could now happen by having a 0 and a 3 and a 0, but also a 1 out of 2 and a 2 out of 1. There's 4 ways this way is going to work. We need to acknowledge all of them. So 0 and the 3 will be a half times by, now a 3 minus 2 is 1, 1 times a quarter is a quarter, so again half times a quarter, add to quarter times a half for the 3 then a 0, and then we'll add on to that the 1, which again we knew to be a quarter, so a quarter, then times by probability of getting a 2, which was a 0, add and the 0 times the quarter. Yes, again, these 0 brackets just make no difference, they'll disappear, but it's good to acknowledge them anyway, just to make sure we're clear and thorough in our own minds. This leaves us, once again, with yet another quarter. For the probability to equal 4, what we can have is either a 1 out of 3, a 3 out of 1, or a 2 out of 2. None of them are going to be consist of 0 anymore. We're far beyond that. It's too high to just have one more number to it. So yeah. So here, if we wanted a 1 and a 3, then we can say that's going to be a quarter times by a quarter, and obviously add a quarter times a quarter for the 3 then the 1. And then for the 2 and 2, again, we have to acknowledge it, 0 times 0. So together, that's going to get us 1/8. The probability of it equaling 5, we already know from down here, that's just going to equal 0, so we don't need to work it through again. And so lastly, we now just have that if the sum of them is going to equal 6, the only way it equals 6 is if we have a 3 and a 3. So that's going to be quarter times by a quarter, which we now get 1/16. If you wanted to double check, you just want to add these all up and make sure they equal 1. Well, they would do. Just, you can put in the calculator if you want. And before we continue, before we actually get to the table, what we could say is that this kind of questioning, this kind of method, may be associated with the word exhaustive. If you see exhaustive associated anywhere, it's basically just saying that we are trying out every single possible outcome. You're looking at every single possibility, every single probability within a given scenario's limited range of x. Anyway though, to the table, so you're now going to want to have 2 rows. So you'll have the top one is just about what your x1 plus x2 equals, but below that we'll then need the probability of the x1 and the x2. We're going to need columns for the 0, 1, 2, 3, 4, 5, and 6. So just quickly draw that up, and then you can put in these probabilities in the respective areas. So quarter, quarter, 1/16, 1/4, 1/8, 0, and 1/16 again. Now from here, just to wrap it up, if we have, so the probability of x plus 1 and x plus 2 being between 1.3 and 3.2, well, for those values, the ones that are between those are the 2 and the 3. So if we were simply to add those probabilities together, the probability that your thing is between the 1.3 and the 3.2 would just equal that sum of 5/16. Okay. If we're happy with that, if we can see how we have therefore used this initial display of your probabilities here to work out the different probabilities of the sums of those x values and therefore put them into a table, let's now just see how you might get along with an example of your own. So what if we had this table given to you here, where we have these x values. Here's x can be 0, 1, 2, or 3 again, just like in the last question. And we're given that the probability of x being any of these is for 0, 0.2, for 1, we just know it's a, for 2 it's 0.3, and for 3 it's 0.25. So your question is to find the value of a, then find the probability that x is greater than 1.2, and then construct a cumulative frequency distribution. So think about how you're possibly going to work out what this missing unknown probability is, how we can then combine any appropriate probabilities to get the probability of x here, and then think what it would mean to have a cumulative frequency distribution table. So pause the video, have a go for yourself, and then press play again when you're ready to compare. So, first of all, what we're going to acknowledge is that, as we said earlier, all the probabilities of a given situation have to add up to 1. Because they've given us that these are the possible x values, we can say that to add up these probabilities must be the total, right? So, we can say that a will be 1 minus the 0.2 minus the 0.3 minus the 0.25. Well, that leaves a being 0.25 itself. So there's an equal probability of getting 1 and 3. Well then, if we're to get the probability that x is greater than 1.2, then that's going to be referring to when x is either 2 or 3. So simply add those two probabilities together and you would get 0.55. And lastly, to get the cumulative distribution, well, what cumulative is saying, if you know just from cumulative frequency graphs, is that we'll be adding up the probabilities as we go, right? So if we were to then have now an x on the top row of our table, but here it was a probability that x is less than or equal to x. So basically adding up probabilities with all the ones before it. If you then have again your 0, your 1, your 2, and your 3, and just draw up the boundaries of your table like so, the probability of being less than or equal to 0 is just the 0.2 because there's nothing else below it. But the probability of x being less than or equal to 1 is the probability of being 0 or 1, so it'd be 0.2, add to the 0.25 we worked out before, so that'd be the 0.45. To be less than or equal to 2 is to be either 0 or 1 or 2. So again, add up all of those. So now add the 0.3 to this, to 0.75. And lastly, less than or equal to 3 is basically the probability of being any of them, which you can already say is 1, or if you take 0.75 and add the 0.25 again, would give you that certainty. Okay. If we're happy with that, let's just then turn to one final question, which is going to, again, build on this idea of the cumulative distribution. So a discrete random variable x has that following probability distribution. The x can be any of 0, 1, 2, or 3, and then the probabilities of that are going to be 0.2, a, 0.3, and b, where a and b are constants. And the cumulative distribution is going to be, so 0, 1, 2, and 3, c, d, 0.78, and E. And from this, we need to find the values of A, B, C, and D. Okay, well, for this, we're just going to be comparing our tables. Because this here is the cumulative, it's all the before, there is nothing below the 0, so this probability here is just going to be the exact same. It's going to be at 0.2. Now then, if in order for us to then say that the cumulative of up to 2 is 0.78. We're saying the probability of 0, 1, and 2 altogether is the 0.78. So what we can do is take away 0.3 and 0.2. That leaves you with 0.28. being your A here. So then for D, you could add those two together to say that it's 0.48. Alternatively, to get D, what you could have said is that if you were to take away the 0.3 here alone, that would leave you with the previous cumulative probability. Again, that would leave you 0.48. And again, you could have taken away the 0.2 to leave you with that 0.28. And then lastly, to get your B and your E, what we have to do is rely on the fact, as we just saw in the previous example, that in the cumulative distribution, the end number always has to be 1. It always has to add up to that. So that's what E has to be. And then finally here for B, we can either do the 1 minus the 0.78, which in this case is going to leave you with 0.22, or in what is basically the same equation, just focusing on it from a slightly different angle, we could say that this row here has to add up all to 1, so 1 minus each of these, again, leaves you with B being your 0.22. When we're just looking at probability distributions like this, we are likely having a table or that other means of representing distribution before with the curly bracket. But then ultimately, it's again just going through and saying, okay, these have to add up to 1. How do I therefore fill in the blanks? Or do I substitute in an x to work out what each of the k's are going to be and so forth? And so long as we're understanding that that's what we have to do, hopefully that shouldn't give you too much trouble.